Welcome to Pallavi Online Tutorials. In today's presentation, we'll discussing about series parallel resistance. With respect to the following points, series resistance, equivalent resistance, voltage across each resistance, current across each resistance, voltage divider rule. For parallel resistances, equivalent parallel resistance, voltage and current across each parallel resistors, then current division rule. Having said so, since observe these two resistances R1 and R2, these two are in series. Now what makes me say that these two resistances are in series? When two resistors are in series, same current I flows through them. Now my question is, what if there was a third resistor R3 connected in this manner? Would the current in this current I the same as this current? Here the current would have been splitted as I1 and I2. So the current through resistor R1 then would not have been same across the current across R2. So then they were, for the third resistor R3, two resistors were not in series. So very important condition is that for the resistances to be in series, same current should pass through them. Same current should pass through each resistor. What happens to the voltage drops? The voltage drops are additive, implies V is equal to V1 plus V2. This V is the applied voltage. Resistances are additive. That is, here we can see that the equivalent resistance for a series resistor is R is equal to R1 plus R2. Power is additive, that is the I square R voltage drop across them can be added. Now the applied voltage equals the sum of the voltage drops. This is as per KVL. This is as per Kirchhoff's voltage law. Now before reading this presentation, all of you should be knowing about KVL and KCL, Kirchhoff's current law and Kirchhoff's voltage law. What is voltage division in series circuit? The voltage division in series circuit is that how is the applied voltage distributed among two resistors, that is called as voltage division. The current I passed through this circuit is nothing but V upon R1 plus R2. Again we can say that this is by our very own Ohm's law. Voltage drop across R1 is equal to R1 into I. Voltage drop across, then R1, again substituting this value of I, we get this value of voltage drop across R1 as R1 upon R1 plus R2 into V. Similarly, the voltage drop across R2 can be said as R2 upon R1 plus R2. Now, what is, in generalizing, we can say that the voltage drop across any resistor is that the value of the resistance itself, total series resistance, into the applied voltage. Now what if there was a third resistor in series? In order to see this, we will see one problem. Now in the given circuit, find out V1, find out V1, V2 and V3. This is three resistors R1, R2 and R3 connected in series. What we are supposed to do, we are supposed to find out the voltage drop across individual resistors V1, V2, V3. Since the five resistances are connected in series, voltage division rule can be used. Now what is the meaning of this sentence? Since they are connected in series, this is used, voltage divider rule can be used only and only for series connected resistors and not for parallel connected resistors. So coming back to our voltage divider rule for three resistors is like that: drop across the resistance is equal to R1, that resistor itself, upon total equivalent resistors, which is the sum of all the three resistors, into the applied voltage. Now some calculations. The voltage drop across this is nothing but 5 by into 60 is nothing but, we can say that 5 upon the sum of all the three resistors into 60. Here 60 happens to be the applied voltage. we find out the voltage drop as 10 volts. Similarly, by applying voltage divider resistors to a 10 ohm resistor, we can see that the value of this resistor is 10 ohm upon total resistance into 60, which turns out to be 20 volts. Then voltage divider rule, to find out the voltage drop across the resistor 3, we see that the resistor is 15 upon total resistance into 60, turns out to be 30 volts. Now if you observe that 10 plus 20 plus 30 is nothing but 60, so our answer is correct. Coming back to our parallel resistance circuit. Now these three resistances are connected in parallel. What made me say that they are connected in parallel? See that the resistors are connected end to end. Resistors are connected end to end. Now these three resistors, the current across if you observe the current across three resistors, the current is getting divided into three resistors. However, the voltage drop across all the three resistors is the same. Same voltage appears across all resistors. V1, this let's call this V1, V2, V3. Drop across all resistors is equal to the voltage drop V. Now the branch currents are additive, that is this I1 plus I1 plus I2 plus I3, it will be equal to the total current I. Conductances are additive. Now here we will see what are the equivalent resistor of a parallel circuit. When three resistances are connected in parallel, this is the equivalent resistance. 1 upon the equivalent resistor is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. This is the value of the equivalent resistance. Now what is 1 upon resistance? 1 upon resistance is nothing but conductance. Conductance happens to be the reciprocal of resistance. So they are telling that conductances are additive, that is sigma t is equal to sigma 1 plus sigma 2 plus sigma 3. Clearly sigma 1 is the reciprocal of R1, sigma 2 of R2 and sigma 3 of R3. Power is additive, that is the I square or losses of all the three resistors are additive. Now coming back to current division rule. What is a current division rule? Current division rule, first of all, current division rule is applicable only if three resistances are in parallel. As the name indicates, how is the current distributed in all three branches of the resistor? That is current division rule. It says that the current in resistor 1 I1 is equal to RT, that is RT is the equivalent resistance, not the total resistance. Don't sum the resistances. RT upon R1 plus RT upon R1 into I. For branch 2, that is RT upon R2 into I, and for branch 3, RT upon R3 into I. What is RT? As I already told you that the total resistance in case of parallel resistance or the equivalent resistance is nothing but 1 upon RT is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. It can be clearly said that the current through each branch is equal to equivalent resistance upon individual resistance into the total current I. This is nothing, I is nothing but the total current source, this total I flowing through all the three resistors. Now to demonstrate this, I will show you one simple problem. Find the current I1, I2 and I3. By current division rule, this is a problem where the total current is 5 ampere. This is a current source again. I1 getting divided into I1, I2, I3 through three resistances of 10 ohm, 20 ohm, 30 ohm. By current division rule, we can say that 1 by RT is equal to, first we find out the total resistance or the equivalent resistance. 1 by RT is equal to 1 by 10 plus 1 by 20 plus 1 by 30. Now I1 is equal to, equivalent resistance has turned out to be 5.45. I1 is equal to 5.45 upon R1. What is R1 in this case? We are finding out this resistance. This is R1. Okay. So this R1 is 10 and phi is the total. Phi is the total current. See, this phi is the total current. Now I1 is equal to 2.727. Similarly, we can find out the current I3 5.45, which is the total resistance upon 30 ohms into 5. Similarly, we can find out I2. Which is turns out to be 1.363 amperes. That completes our theory part. In the next presentation, we will be discussing about series parallel resistance problems, and one additional concept will be taught, that is the short circuited branch. That is, how do you find out a resistance when when there is a short circuit branch between the resistors. Thank you very much.